Good morning. This is Dr. Divya Bartaria, Head of Corporate Relations and Associate Professor in Chemistry, United Group of Institutions, Allahabad. So, welcome to this first session of chemical bonding, which is related to molecular orbital theory. So, today it is assumed, before I start my session, it is very much assumed that all of you have basic idea of chemical bonding, different types of bonds, covalent bonding and modern concept of a covalent bond. Suppose I ask you a question, what is the modern concept of a covalent bond? So, you may recall in your memory that a covalent bond is formed by the overlapping of atomic orbitals. Now, today it is also assumed that you have the basic idea, conceptual idea of hybridization, how the hybrid orbitals are formed, what is the process of mixing of orbitals and how there is redistribution of energy. So, all of us know today that this molecular orbital theory is actually related to covalent bonding. Therefore, it is important to know the differences first between valence bond theory and molecular orbital theory. Further, in this session, we will try to emphasize upon the assumptions as well as the applications of molecular orbital theory. So, let us start with our agenda. So, today's agenda will cover basically 5 important points you can see here. First, what are the differences between valence bond theory and molecular orbital theory? What are the basic assumptions of molecular orbital theory? Then what is LCAO method, that is linear combination of atomic orbitals, and how there is formation of bonding molecular orbitals and anti-bonding molecular orbitals, what are the features of bonding and anti-bonding molecular orbitals, and then at the end we would be discussing or taking an overview of the entire lecture. So, here you can see that when we talk about the differences between valence bond theory and molecular orbital theory, so you can see that in the very first point it has been mentioned that as per the valence bond theory, when two atomic orbitals overlap, then actually when there is a process of overlapping, two atomic orbitals do not lose their individual identity. For example, I can show you here that if there are two atomic orbitals A and B, and when they enter into the process of overlapping, you can see that these two atomic orbitals overlap. Now, if each of the atomic orbital contains one electron, then both the electrons pair up and they remain in this shared pair of region, this shared region. And in that way, you can see that these two atomic orbitals do not lose their individual identity, or you can see that these two atomic orbitals retain their individual identity. However, as far as the difference is considered, you can see that in molecular orbital theory, this diagram clearly represents that after the process of overlapping, both the atomic orbitals, both the overlapping atomic orbitals lose their individual identity, leading to the formation of molecular orbital. Now, here you can see that this is polycentric molecular orbital. It has been mentioned over here, forming the polycentric molecular orbital, right. So, what does this mean? This polycentric molecular orbital contains now two nuclei. Now, when we come to the second point of difference, you can see that according to this theory, that is valence bond theory, only the half-filled atomic orbitals of both the overlapping atoms enter into the process of overlapping. For example, let us consider two atoms of lithium. Lithium has electronic configuration 1s2, 2s1, right. This is the electronic configuration of lithium atom. So, when there are two atoms which are going to overlap each other, so there will be another atom 1s2, 2s1. Now, as per the valence bond theory, only the half-filled atomic orbitals of both the atoms enter into the process of overlapping. So, this has been mentioned over here. But according to molecular orbital theory, it has been said that all the atomic orbitals of all the energy levels of both the overlapping atomic overlap, they enter into the process of overlapping. So, all the atomic orbitals are entering into the process of overlapping as per molecular orbital theory, while in case of valence bond theory, you can see that only the outermost half-filled atomic orbitals enter into the process of overlapping. Now the third point of difference is that this theory, that is valence bond theory, fails to explain the paramagnetic character of oxygen molecule, and also it is not able to explain the formation of H2, H2 plus or odd electron molecule or ions. But on the other hand, molecular orbital theory is very much successful in explaining the paramagnetic character of oxygen molecule and the formation of odd electron molecules or ions such as H2, helium 2 plus and so on. Now, let us come to the basic assumptions of molecular orbital theory. This theory was given by Hund and Mulliken in 1932. So, as per this theory, and we have already discussed when we were discussing the points of differences between valence bond theory and molecular orbital theory, the first important assumption is that when nuclei of two atoms approach each other, their atomic orbitals overlap, they completely lose their individual identity and lead to the formation of polycentric molecular orbitals. This is the first point that you can see here. Now, second assumption is that each molecular orbital is described by a wave function psi, which is also known as molecular orbital wave function. In the next slide, we will be discussing about the mathematical representation of wave nature of electron, and that is why we are using this term wave function here. So, each molecular orbital is described by a wave function psi. Now, the third point says that psi is such that psi square represents the probability density or electron density. Another basic assumption is that each psi is associated with a set of quantum numbers which determine the energy and shape of the molecular orbitals. Now, each psi is also associated with a definite energy value, and the total energy of the molecule is the sum of the energies of the occupied molecular orbitals. We will be finding this point, this assumption, when we will be discussing about the applications of molecular orbital theory. Now, all of us know that electrons fill the atomic orbitals, and in the same way, electrons fill the molecular orbital, following the principles of Bau's principle, Pauli's exclusion principle, and Hund's rule of maximum multiplicity. So, all these rules are being followed here as well. Each electron in a molecular orbital belongs to all the nuclei present in the molecule. So, dear students, you can see that these are the basic assumptions of molecular orbital theory. All these points are very much important to be understood by all of you. Now, moving ahead, when we come to the linear combination of atomic orbitals, we are using this term LCAO method. So, this is actually the mathematical process of combining atomic orbitals to generate molecular orbitals, and this is known as linear combination of atomic orbitals. Now, this wave function describes the wave-like properties of an electron. You can see that when both the electron waves are present in the same phase, then here you can see then peaks are lining up with the peaks. So, what is the resultant wave? The resultant wave is of high amplitude, while when both the waves are out of phase, they are not in phase, peaks line up with the troughs. So, there is a kind of destructive interference. Here there is constructive interference, while here there is destructive interference. So, destructive interference leads to the formation of a wave with less amplitude or even zero amplitude. So, whenever we will be considering the linear combination of atomic orbitals, then we will have to keep it in mind that it has wave-like property, and then there may be constructive interference or there may be destructive interference. So, it leads to the formation of two types of molecular orbitals. Let us see how. Here this slide shows that suppose there are two atoms, one is hydrogen and the other is hydrogen. So, this is an example of formation of hydrogen molecule, H2 molecule. So, here what we can see that there are two atoms of hydrogen, each containing one electron, and when they overlap, when they enter into the process of overlapping, you can see that LCAO gives an approximate but satisfactory idea about molecular orbitals. So, there is linear combination of atomic orbitals, two atoms approach each other along the same line, overlapping occurs, and it leads to the formation of molecular orbitals. As we have discussed, there are two types of molecular orbitals which are formed here. One is bonding molecular orbital, which is formed due to the constructive combination. You can say that it is combination by addition. So, it leads to the formation of bonding molecular orbital. However, when both the atomic orbitals are present in the opposite phases, they are out of phase, then it leads to the combination by subtraction. You can see here. So, it is the formation of anti-bonding molecular orbital. Here also you can get a clear idea of formation of bonding and anti-bonding molecular orbitals. You can see that this is additive combination, this is subtractive combination. Here you can see the shapes get distorted. Here the bonding molecular orbital is being formed. We can consider other atomic orbitals as well as. So, we are going to consider the SS overlap at first. Overlapping of SS atomic orbitals. So, friends, when we consider the overlap of two s orbitals, all of us know that s orbital is spherically symmetrical, right. Now, when we consider that both the atomic orbitals are present in the same phase, for example, if I consider plus, this is also having the same phase, and then they enter into the process of overlapping, then it leads to the formation of polycentric molecular orbital. This is combination by addition. This is actually the combination by addition. However, when both the overlapping atomic orbitals are not present in the same phase, that is, one is having plus and the other is having minus. So, it shows the having the atomic orbitals in the opposite phases. Now, what happens here? The shapes get deformed. So, the electrons flow in this direction, and here we can see that it leads to the destabilization state. So, it is the formation of anti-bonding molecular orbital, and this is bonding molecular orbital. As we have discussed, the bonding molecular orbital has lower energy while anti-bonding orbital has higher energy. Now, let us move ahead. If we have considered the combination of s orbitals, we can also consider the combination of p orbitals, right. Now, it has been assumed that there are 3 p orbitals. We can see that there are 3 p orbitals. If this is, suppose this is the molecular axis, that is the z axis, and this is the x axis, then this will be y axis, right. Now, considering z axis as the molecular axis, there is one p orbital, this is pz. There is another p orbital perpendicular to it, this is px, and similarly this is py, right. So, here you can see that there are 3 p orbitals, px, py and pz. So, here in this particular picture, it has been considered that px atomic orbital is present along the molecular axis. So, when along the molecular axis 2 px atomic orbitals approach each other, so in LCAO method, again we will be able to get two types of molecular orbitals. If both the atomic orbitals are present in the same phase. Same phase here means that the overlapping lobes are present in the same phase. For example, I am going to clarify it here. This is plus, this is minus, right, and here you can see this is plus and this is minus. So, what we can find here is that both the overlapping lobes are present in the same phase. So, here it leads to the formation of sigma px, sigma 2 px, sigma 3 px and so on. But if the overlapping atomic, suppose this is plus and this is minus, obviously this would be minus and this would be plus, then what would happen? Then there would be no interaction, this would be the lesser, smaller lobe and this would be the bigger lobe, and in that way a kind of repulsion occurs. This leads to destabilization and we get the anti-bonding molecular orbital. So, this is sigma star, asterisk shows that it is anti-bonding molecular orbital. Friends, we have considered here px as to be present along the molecular axis. Now, when we consider the another p orbital which is present perpendicular to the molecular axis, here you can see this is the molecular axis and both the atomic orbitals are present perpendicular to the molecular axis, and in that particular case, if both the atomic orbitals, here you can see that this is plus, this is plus, this is minus, this is minus. So, in that way both the atomic orbitals get overlapped and it becomes in this manner, one bigger lobe and one bigger lobe. This is plus plus overlap and this is minus minus overlap, right. So, this diagram shows the formation of which molecular orbital? Bonding molecular orbital. Now, when there is sidewise or lateral overlap, obviously we know that it leads to the formation of pi. So, if 2 px atomic orbitals are here, then it leads to the formation of pi 2 px. Suppose this is 2 px and this is 2 px, then it will be pi 2 px. And when they are overlapping in this manner, that both the atomic orbitals or the overlapping lobes are present in different phases, then obviously there wouldn't be proper overlap, there would be destabilization leading to the formation of anti-bonding molecular orbital, then it would be pi star 2p x, right. I hope it is very much clear to all of you. Similarly, we can consider another orbital, p orbital. Which one is left? Py. Suppose we have considered pz as present along the molecular axis, then both the rest orbitals like px and py would be present perpendicular to the pz atomic orbital. Yes, there may be another combination as well. We have considered SS overlap, we have considered PP overlap. So, we can have a discussion on SP overlap as well. So, here also it is very important to understand that which atomic orbital you are going to consider to be present along the molecular axis. Suppose we have considered pz as the atomic orbital which is present along the molecular axis, then what will happen? S plus S will lead to sigma S and sigma star S, right. This is very much clear to everyone. Similarly, when there is pz, suppose 2 pz plus 2 pz atomic orbitals are there, then it would lead to the formation of sigma 2 pz and sigma star 2 pz, right. And when we talk about the px, then 2 px and 2 px would lead to the formation of pi 2 px and pi star 2 px. Likewise, pi 2 py and pi star 2 py. So, the question is that which atomic orbital, which p atomic orbital would enter into the process of overlapping with S. Here it is very important to understand that since S is spherically symmetrical, it is present along the molecular axis. If this is the molecular axis, then you can easily see if this is pz, then pz and S will combine together. Again the overlapping would occur, S plus pz would lead to the formation of sigma molecular orbitals. All of us know that there is end to end overlapping, so it would lead to sigma spz and sigma star spz, right. And in books it may be mentioned that px is present along the molecular axis, then very easily you can consider sigma spx and sigma star spx. It depends upon you, whatever convention do you use, it should be very much clear to everyone, to you yourself and to your teacher. Now, when we consider the formation of S and pz, it is very much possible, we have understood. Now, another question we would like to discuss when we move ahead. Okay, before we come to the question, we would definitely consider that what are the features of bonding and anti-bonding molecular orbitals. Very easily you can understand. Suppose psi A and psi B are the wave functions of two atoms A and B respectively. So, we are talking about two atoms because atoms A and B are going to overlap each other in order to form any kind of molecule or the molecular orbital. So, if the lobes of the combining atomic orbitals of the same sign overlap, as we have already discussed, then the bonding molecular orbital is formed, and then the wave function of that bonding molecular orbital may be represented as psi plus. So, this is psi plus, wave function of the bonding molecular orbital. Now, here you can see psi plus may be represented as psi A plus psi B, right. Why? Because Psi plus represents the bonding molecular orbital, and bonding molecular orbital is formed because of the additive combination of two atomic orbitals having the wave functions psi a and psi b respectively. I hope it is very much clear to all of you. Now consider the second feature. If the lobes of the combining atomic orbitals with the opposite signs overlap, what would be formed? There would be the formation of anti-bonding molecular orbital, which may be represented as psi minus, as we have represented bonding molecular orbital as psi plus. Similarly, we can represent anti-bonding molecular orbital as psi minus. So, how can we represent psi minus? Psi minus is equal to psi a minus psi b. Psi a plus psi b, this is combination by addition, and psi a minus psi b, this is combination by subtraction, right? Now, the energy, we have considered the energy part as well. So, the energy E plus of the bonding molecular orbital psi plus is always lower than the energies of either of EA or EB. Similarly, the energy E minus of the antibonding molecular orbital psi minus is higher than either of EA and EB. We have already discussed this. So, this is a very good representation of features of bonding molecular orbitals, right? Okay. So, electron charge density. In the assumptions part, we have already discussed that if molecular orbital's wave function is psi, then psi square will represent the electron charge density. So, here you can see that this is psi plus square, which represents the electron charge density of bonding molecular orbital. So, what it would be? Psi plus square is equal to psi a plus psi b whole square, which is equal to psi a square plus psi b square plus 2 psi a psi b. So, what we can conclude from here? We can very easily conclude that the electron charge density in bonding molecular orbital is greater than the electron charge density in any of the overlapping atomic orbitals, right? It is very much clear. It can be clarified with the help of this diagram as well. When both the atomic orbitals overlap, what will happen? The electrons distribution would be like this. This is nucleus, right? This is nucleus, and the electrons are distributed in this manner. So, what we can see here, the electron charge density is maximum. Electron density is maximum where? In between the nuclei. So, this is the same conclusion that we have drawn here. The electron charge density in bonding molecular orbital is greater than the energies or the electron densities of either of the atomic orbitals. This leads to the conclusion that we have already understood. Similarly, what we can find here, psi minus square is equal to psi a minus psi b whole square, which leads to the conclusion that the electron charge density in antibonding molecular orbital is less than the energies of either of the atomic orbitals. Here you can see that the electrons are distributed in this manner. So, in between the nuclei in case of antibonding molecular orbital, so electron density is minimum, right? So, what does this mean? Minimum means the shield is removed, the electronic shield is removed, and therefore, both the nuclei are exposed to each other. Nuclear repulsion is high, and therefore, it leads to the repulsion and destabilization of the bond, and therefore, it is also known as the antibonding molecular orbital. So, we have already concluded. Now, at the end, this is very important to understand that when we are going to study the overlapping of atomic orbitals, so what are the conditions for the combination of atomic orbitals? So, first of all, it is very much clear, it must be very much clear to everyone that the energies of the atomic orbitals must be similar in magnitude. For example, if we consider the formation of homonuclear diatomic molecule, we will be considering the formation of homonuclear diatomic molecule in the next session. So, here when we consider the homonuclear diatomic molecule, that is A2 or Li2 or N2 or O2, we can see that 1s plus 1s combination is not possible. This is not possible. Why? Because there is a difference in energies. Similarly, 2s and 2p combination is not possible because there is a difference in energies. So, the first condition is that the energies of the overlapping atomic orbitals must be of similar magnitude. Similarly, while in the formation of heteronuclear diatomic molecules, we can see that 1s and 2s combination is possible. Why possible? Because there may be similarity in their energies. Similarly, 2s and 2p combination is possible. Why? Because their energies may be similar, right? Another important thing is that the atomic orbitals must have the same symmetry about the molecular axis. So, the energies must be remain the same. Similarly, the symmetry must be the same, and these are the conditions. And also, this is very important to understand that when the extent of overlapping is high, is sufficient, then the atomic orbitals combine. So, these are 3 conditions which you have understood today. So, at the end, there is only one question for today. Considering z axis as the molecular axis, which of the following combinations is not possible? So, here you can see these are the options. These are the options that have been given. So, just think, give a thought in your mind that whatever you have studied today, on the basis of that, considering z axis as the molecular axis, this is the z axis, this is the molecular axis, which of the following combinations is not possible? So, S and S possible or not possible? Yes, this is possible. Px and Px possible or not possible? Yes, it is possible, because we can consider the overlapping of Px and Px atomic orbital. Similarly, Py and Py possible or not possible? Yes, it is possible. Why? Because this is also a sidewise or lateral overlapping of atomic orbitals. Then S plus Pz possible or not possible? Yes, it is possible. Why? Because we have it in the question, it has already been mentioned that considering z axis as the molecular axis. So, here you can see that Pz is this and S combination is very much possible, right? And similarly, Pz and Pz combination is possible or not possible? Yes, it is possible. Why? You can show in this manner, Pz and Pz, this is the molecular axis. So, Pz and Pz combine together and they lead to the formation of sigma molecular orbitals. Now, last option, S plus Px possible or not possible? No, this is not possible. So, friends, this option may be selected as the best option, and you can give a very nice description by showing this diagram that when we talk about Px, Px is like this is Px, and when we talk about S, then definitely S is like this, right? So, here you can see this is plus, this can only be plus or even minus, and this is plus lobe and this is minus lobe. So, here you can see because of different symmetries of both the overlapping atomic orbitals S and Px differ from each other. So, this is not possible. Again, another reason is that this is plus plus overlap and this is plus minus overlap, right? So, both the overlaps cancel each other. So, this combination is not at all possible considering z axis as the molecular axis. So, friends, today we have taken an overview of molecular orbital theory. So, when we take an overview, we can see that today we have done a comparative analysis of valence bond theory and molecular orbital theory, and also we have done a study on LCAO method. We have understood the basic assumptions of molecular orbital theory and how the bonding and molecular orbitals, anti-bonding molecular orbitals are formed. Similarly, we have understood that LCAO actually gives an approximate but satisfactory idea of overlapping of atomic orbitals and henceforth for the formation of molecular orbitals. So, we have considered the overlapping of various atomic orbitals. You can see that how we have drawn a conclusion that how the SS atomic orbitals overlap, how the PP atomic orbitals overlap, and what kinds of combinations are possible. Also, we have discussed the features of bonding and anti-bonding molecular orbitals. So, this is all for today. See you in the next session on chemical bonding. Thank you very much.